So the first topic that we are going to discuss today is contravariant tensor. Contravariant tensor. Contravariant tensor. Okay. What are contravariant tensor? Contravariant tensor haragadi at a point P on a manifold, there is an object, and this object has n number of components. So at a point P, I give manifold in this manifold at the point P. At this point P, we have an object, and this object has n number of components. And this n number of components, they are represented by capital A to the A superscript A. Capital A superscript small a. Small a can take values from 1, 2, 3, 4, and so on till n. So A can take values from 1, 2, and so on till n. So on the manifold at the point P, I have an object, and this object has n number of components, and the n number of components are given by capital A superscript A. And if this n number of components, if these components change under a coordinate transformation, if this n number of components, they change according to this rule, A superscript A bar, this is equal to del x A bar del x B A B. Okay, so on this manifold at the point P, I have an object, and this object has n number of components. And this n number of components are represented by A superscript A. Now we take two different coordinate systems. Amana bar coordinate system, amana unbarred coordinate system. Bar coordinate system the ladiba ngasai A hariba kanojigi objects component chinduna A superscript A bar. So these are the components of the object in the barred coordinate. These are the components of the object in the unbarred coordinate. So when I transform from bar coordinate to unbarred coordinate, if the components transform according to this rule, Sigi rule is follow the if the components transform according to this rule, then we say that this capital A superscript A, these are the components of a contravariant tensor or a contravariant vector. Let us say vector. So contravariant vector have the under a change in coordinates. If the components transform according to this rule, then we say that these are the components of a contravariant vector. So what are the two coordinates? I'm on a bar coordinate, I'm on an unbarred coordinate. These are the components in the unbarred coordinate. These are the components in the barred coordinates. This quantity, this can be represented by capital gamma A bar CB AB. So this is represented by capital gamma. And these partial derivatives, they are evaluated at this point P. I don't know what is the contravariant vector hierarchy. At the point P, if I have an object which has n components, and if the components that transform according to this rule under a coordinate transformation, then these n components, they are the components of a contravariant vector. Similarly, we define a covariant vector. Covariant vector. Covariant vector Sisu, at the point P on the manifold, I have an object, and this object has n number of components, subscript one A subscript A, and Here also A can take values 1, 2, and so on till n. So n number of components. And these components, if they transform according to this rule, A bar, this is equal to del xb by del x A bar AB. So under a change of coordinates from the unbarred system to the barred system, if the components of the object transform according to this rule, then we say these are the components of a contravariant vector. So this is about covariant vector. This is a transformation rule for, this is the transformation rule for contravariant vector. This is the transformation rule for covariant vector. And this partial derivative, it can also be represented by capital gamma B A bar with subscript B. So this is about covariant vectors. And let us look at examples of covariant vectors and contravariant vectors. One simple example of contravariant vector. Example of contravariant vector. So one basic example of contravariant vector is the tangent vector to a curve. I have a curve gamma. This is a curve gamma. The tangent vector, this vector, the tangent vector to the curve at the point B. This is an example of the contravariant vector. This curve, it can be given parametrically by x superscript A is equal to, it's a function of the parameter t. T is some parameter. T is some parameter, and then this xa, these are the coordinates of the point B, and these are differentiable functions of t. These are differentiable functions of t, and this xa, they are the components of the point P. At its point of the curve gamma, the derivative which is given by xa dot. Xa dot. This means the xa by dt. Xa dot means the xa by dt. So at its point of the curve gamma, the derivatives, that is xa dot, these are the components of a vector. This xa dot, that is dxa by dt. These are the components of a contravariant vector. And let us see whether it actually follows the transformation rule for contravariant vector. Sigi xa dot, sigi component sing contravariant vector component ni hairiyebo. Although they should follow the transformation rule for contravariant vector. Sigi rule will follow. So let us see whether they follow this transformation rule or not. So in the bar coordinate system, x a bar, the coordinates of the point will be x a bar in the bar coordinate system. Okay, this is actually x a bar. This bar coordinate system x a bar, this can be expressed in terms of the unbarred coordinate system, x1t, x2t, and so on till xn t. This bar coordinate system xa, this can be expressed in terms of the unbarred coordinates. So I need a differentiation with chain rule x a bar, x dot a bar, have to know dx a bar by dt. This is equal to del x a bar by del xb dxb by dt. This is what we get from the chain rule. Chain rule of differentiation. We get that derivative of dx a bar with respect to dt is the partial derivative of dx a bar with respect to dxb, then dxb with respect to dt, and summation over all possible values of b. This is summation over all possible values of b. Here, I have not used the summation sign because I am assuming that we are using the Einstein summation convention. Einstein summation convention. Einstein summation convention. And what is the Einstein summation convention? Einstein summation convention, it says that if two indices are the same, I'm on an upper index, I'm on a lower index. If two indices are the same, then they are summed over all possible values. So here Bj is the repeater in the call. So B is the same here. That means we're taking sum over B for all possible values of B. That is sum over B from 1 to n. And this we already know dx bar del x bar by del b. This is nothing but gamma a bar b by gamma a bar b, and dxb by dt. This is x dot b. So when we compare this transformation rule with the transformation rule for contravariant tensors, we find that they are the same. Contravariant transformation rules. So x a bar dot is equal to gamma a bar b x dot b. So it follows the same transformation rule. Therefore, it shows that dx by dt, dx by dt, that is the tangent vector to this curve. It is an example of a contravariant vector. Let me pause the recording here. So now let us look at an example of covariant vector. So gradient of a scalar field is one example of a covariant vector. This gradient, this scalar field, let us call it phi. So in any coordinate system, this scalar field phi can be regarded as a function of the coordinates. In this way, phi is a function of the coordinates xa. And we can form partial derivatives of this phi with respect to the n coordinates. So the partial derivatives del phi by del xa. This is represented by del subscript a phi. So del phi by del xa. So I need del subscript a phi. So here a can take values, a can take values 1, 2, 2 dot n. So I have a scalar field phi, and these are the components of the gradient of the scalar field. Now let us see how these components transform under a coordinate transformation. So let us transform the coordinate from the unbar to the bar coordinate system. So in the bar coordinate system, this phi again can also be regarded as functions of xa bar. And then the partial derivatives of this phi with respect to the bar coordinates, that is del a bar phi. Del a bar phi means del phi by del x a bar. This is the partial. These are the components. These are the components of the gradient with respect to the bar coordinate system. These are the components of the gradient with respect to the unbarred coordinate system. So how are these two, this and this, how are these components related? From the chain rule, what do we get? From the chain rule, we have del phi by del x, sorry, x a bar, del phi by del x a bar. This is equal to del phi by del xb by del x a bar. Del phi by del x a bar is del phi by del xb by del x a bar. Here also we have used the Einstein summation convention. That is, the index b is repeated in the numerator and the denominator. That means we are taking the sum of these terms for all possible values of b from 1 to n. This means, meaning the summation over b from 1 to n del phi del xb by del x a bar have. Here b is repeated, so I am taking summation over b from 1 to n. In Einstein summation convention, we simply remove this summation sign and we assume that we already know that the summation sign is there. We're simply removing it to save space. Einstein summation convention, the summation already the summation assume any index up lower repeat we are assuming that it is summed over. So this is equal to this. That means del xb by del x a bar del phi by del xb. This is del phi by del x a bar. But this is how the components of a covariant vector. Transform. See transformation rules I can say covariant vector की transformation rules compared to kind of submanara. That means the components of the gradient of a scalar field, they transform like the components of a covariant vector. So covariant vector की basic example gradient of a scalar field ni. Contravariant vector की basic example na the tangent to a curve at a point. Suppose that we have at the point P of the manifold M, say that let us draw the manifold M again. At the point P, we have here n to the power r plus s. We have our associated n to the power r plus s quantities. So point P is the object object to n components high covariant vector, contravariant vector high. And then the object object this many components later. The object has this many components. Aduga object represent tau magi superscripta a1 dot ar subscripta b1 dot bs. So there are r number of superscripts and s number of subscripts. Sigumba object so for different values of a, a1 can take values from 1 to n. A2 can also take values from 1 to n. So in total, this object has this many number of components. Object this many number of components later. Under a coordinate transformation, see objects components if they transform according to this rule, the tau a1 bar dot 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 ar bar, b1 bar dot 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 bs bar. This is equal to gamma a1 bar c1 dot 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 gamma ar bar cr. So move gamma b1 bar d1 dot 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 gamma bs bar ds tau c1 dot 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 c1 c2 cr book d is na d1 dot 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 ds box. Sigi katang yeng but complex malam be but sigi upper index mayam just yeng kanda contravariant tensor amana transform to minus transform to sigi upper index na contravariant vector amna transform to minus transform to lower index singina covariant vector na transform to minus transform to adu this quantity these are the components. These are the components of a type. These are the components of a tensor of type. Tensor of type. Mathak kya lay a1 dagi sum chalaga ar bok lay. Mathak r makhada b1 dagi oraga bs bok lay. Type rs ka. So I have a quantity which has rn to the power r plus s number of components, and the components of the quantities are represented by this symbol. The components, if they transform according to this rule, these are the components of a tensor of type r, s. Complicated tensor maximum r s values 4 the values of r and s can go up to 4 but not beyond 4 core study. So for example keep it here. For example hai example the components of a type 2-0 tensor. The components of a type 2-0 tensor transform. The components of a type 2-0 tensor transform according to the rule tau a bar b bar is equal to gamma a bar gamma b bar. Bar ni maksidi matak tele ni makatana c ma thamo d ma thamo adagi tau c d. Here we go. This is how the components of a tensor of type 2-0 transform under a coordinate transformation from the unbarred coordinate system to the barred coordinate system. I think tau have a object tau cd these are the components of the object in the unbarred coordinate system. And tau, a bar, b bar, these are the components of the same object in the barred coordinate system. How are these two components related? These components are related through this equation, through this transformation rule. So already these are the components of a type 20 tensor. Components of a type 1,2 tensor. Components of a type 1, tensor 2D transform according to what to transform S. So I get tau A bar B bar C bar. This is equal to A bar yam thamo gamma sida B bar yam thamo B bar gamma C bar yam thamo A bar is D yam hapazi D. So this is tau A bar is mahuta D yam layani B bar gi mathakta E yam hapazi. So makas the E yam layani C bar gi mathakta F yam hapazi. This is the F yam layani. So this is how the components of a type 1,2 tensor transform under a coordinate transformation. Sigi, in general, this is how the components. In general, this is how the components of an RS type tensor. R plus S. R plus S is sometimes called the rank. So rank or order of the tensor. This R plus S is sometimes called the rank or order of the tensor. There we go. Okay. Stop the recording here.